Okay, let's jump right in. Today we're going deep into the nervous system of modern internet.
Hmm.
We're looking at a piece of hardware, the Thor broadcast F-PLC-1x8 fiber optic coupler splitter.
Right. And what we're really looking at is a definitive passive optical component.
So our mission here is to cut through the jargon and figure out how this little box acts as like a central hub for all our data.
Exactly. The name itself, FPLC 1x8, kind of gives the game away. It's a splitter. It takes one fiber optic signal in
And splits it.
and splits it perfectly across 8 separate outputs.
Yeah.
That 1x8 configuration is the whole point. It's the intersection where the main line fans out to everyone's home.
Okay, so if it's acting as this sort of traffic cop for light signals, where does this piece of hardware actually live? Are we talking a nice climate-controlled data center?
Not usually. That's the key. The applications tell the story. This thing lives out in the field.
In the field.
Yeah. It's essential for what we call fiber to the home, or FTTH, and the bigger category fiber to the X. It's the silent engine in passive optical networks, GPO NAND, specifically which, rely on unpowered splitters to cut down on maintenance.
That makes so much sense. So it has to be tough. Now, this is where it gets interesting for me. The physical connections, the source details, 4 different connectors, LC, SC, ST, and FC. That seems messy. I mean, if the LC connector is the best for high density, why are we still juggling 3 others?
That is an excellent question, and the answer is legacy. You're right, the LC with its tiny 1.25 millimeter ferrule is king for density.
Right.
But networks are built over decades. You still have tons of older infrastructure out there using the bigger SC snap-in or the old ST bayonet twist lock.
The twist lock, right.
And even the screw-type FC. So the fact that this splitter is available with all 4 just shows the manufacturer gets it. Technicians in the field need that backward compatibility.
Got it. So it's a logistics headache, but a necessary one. Okay, we've got the physical side down. But what about the signal itself? How do you keep it pure? The source flags a low insertion loss of 4 dB. Why should we care about that specific number?
That 40B figure, it's all about the trade-off. Insertion loss tells you exactly how much optical power you lose when you split the signal 8 ways.
So it's a guaranteed loss.
It is, and since every decibel you lose shortens the distance your signal can travel, keeping that number as low as possible is, well, it's everything. It's the difference between a working network and a failed one.
And there are other factors too, right? Like PDL.
Yes, exactly. Low polarization dependent loss. That basically measures how stable the signal is no matter how the light is oriented. High PDL means errors, so you want that rock bottom.
Okay, I have to bring this up. The temperature range. It says here it's stable from plus 85 degrees Celsius all the way down to a frozen minus 40.
Yeah.
I mean, how is that even possible for something that relies on micron-level precision?
That durability is its core promise, isn't it? It comes down to material science. You're using things like G657A fiber, which is super resistant to bending, and you're building to really demanding standards.
Like the TLC certification it mentions.
That's the one, YD 1117-2001. The certification guarantees it can be bolted to a pole in the desert or, northern Alaska and just work for years.
This brings up a question of scale then. We're looking at a 1x8 model. Is that it? Is this a one-trick pony?
Not at all. The underlying tech is massively scalable. Our focus is the 1x8, but this planar light wave circuit technology can go from a simple 1x2 split all the way up to a complex 2x64 configuration.
Wow.
So the same core design can power a small office LAN or a massive citywide network.
So if we boil it all down,
Right.
what we have here is a super robust rack-mountable tool that takes one pure signal and reliably shares it with minimal loss, no matter if it's boiling or freezing outside.
That's it, exactly. They really are the unsung heroes powering your high-speed internet right now.
Right.
The final takeaway is that our ability to do everything we do online, from streaming to video calls, fundamentally rests on these simple passive boxes that work perfectly in conditions that would destroy almost any other piece of tech.
So here's a thought to leave you with. Considering the sheer complexity of managing all those different connector types, the snap-in, the twist lock, the screw-on-in, a huge deployment, what do you think is the single biggest challenge in keeping a network like that running smoothly across that insane -40 to plus 85 degrees Celsius range? Something to chew on.